Welcome back. Yesterday we talked about perimeter of polygons. Today we're going to expand that to the perimeter of a circle, which is called circumference. So there are two circumference formulas. You worked with them quite a bit, probably in 8th grade. But the first one is pi times the diameter, or you could also use 2 pi times the radius. Because 2 times the radius is the diameter, these formulas are interchangeable. Whichever one you feel more comfortable with is the one I would use. So with the first example, they give you an equation of a circle, so we're bringing that back into play, and they're asking you which one is closest to the circumference. So reminder, the center of the circle is embedded with the x squared and y squared, so it's going to be 0, 0, because there's no shift. And the 25 represents the radius squared, so to undo that, I took the square root, therefore the radius is 5. All I really care about is using the radius. I chose to use the formula 2 pi r, just because I have the radius, and I put this in my calculator, so 2 times pi times 5 to the nearest tenth ended up being 31.4. We can also combine the idea of circumference with polygons. So again, another fencing problem. We're talking about fencing a garden. It has a rectangle and then a semicircle attached to it. So that's the key here. So I found the circumference. Again, you can either use pi times the diameter or 2 pi r. In this case, because they gave me the entire diameter, as this is a rectangle, these sides are equal, I just put it into this formula. And if you think about it, a semicircle would be half the length around. So I divided that by 2. So now my semicircle is 6 pi, or you could put that in your calculator and it'll compute the decimal for you. Notice I only just divided the 2 into the 12. And then the perimeter, I want to add all the sides that make up that garden. So definitely 17, a 12, a 17, and then a semicircle of 6 pi. When you put that in your calculator, it will compute around 65, and it says nearest foot, so I put feet on there. So stepping it up a little bit, say you don't want to find the entire circumference, but a portion of the circle. So, and it might be a portion other than the semicircle. I cannot get this to go down. There we go. It might be a portion other than a semicircle or a quarter circle. You can find the length of any part of the arc, we call it the arc length, of any circle, as long as you know the central angle and the radius. So here's some key vocabulary. So a portion of the arc is called the arc length. So far, we've talked about central angles. So this represents the central angle there. That's actually the letter theta. That the central angle measure has the same number of degrees along here. I don't care so much about the degrees this takes up. I want the length now. However, I can think of the arc length as being proportional to this angle in the entire circle. So I'm going to use circumference, central angle, and radius. A key word here, it looks like a wedge in layman's terms. This looks like a wedge or a slice or a piece of pie, piece of pizza. This is called a sector. So on the back, this is the bulk of the new information today. I don't want to confuse you with all that's going on here, so let me break it down for you. In the past, I've taught arc length, which we denote with S. Okay, it comes from the Greek word spadium, which starts with an S, so we've chosen that in math, with these two formulas. They're the same formula. However, I found that to be really confusing after trying that for a few years. So last year I modified that. Didn't have time to change this lesson though, to this formula up here. So basically, we're just going to look at a proportion, and we're going to do a little bit of cross multiplication. On this side of my proportion, I put S. That's going to denote this arc length. C is the circumference of the entire circle. So basically, I'm just saying this little piece compared to the entire thing, and then I'm comparing that to the degrees that that wedge or that sector takes up. So it's going to be x degrees, and that's going to help, the central angle will help you with that, compared to the entire circle, which is 360 degrees. So when we look at example 3, I took that to really help me with the arc length piece and ignored the information in the rectangular box. So this example has a lot going on. The first thing I want to look at is making sense of this idea of arc measure versus arc length. arc measure, we've already done that. We know that if the central angle is 60, this arc takes up 60 degrees of the circle. So that would be considered the degree measure, the arc measure, any of those terms. So both these circles, all circles are similar. But both these circles show you a sector that takes up 60 degrees of the arc. The arc length, though, will definitely differ. This one's going to be smaller than this one in terms of length. So what I did, I'm going to try my best to scroll this down carefully. There we go. So what I did is I went after circle C first over here. So I set up my general equation. S is arc length compared to the circumference. And I'm saying that equal to the degrees the arc takes up compared to all the degrees in the circle, 360. I chose to do my work on the side here. It's up to you. You can put it right in here as you go along. To me, I just like the look of it better once I figure out the decimal place. So I said the circumference is 2 pi r, radius is 2 here, so 2 times pi times 2. If you just multiply these together, you get 4 pi. If I put that in your calculator, round to 100th, that's fine. It'd be 12.56, so I replace the c with 12.56. I know that if this central angle is 60 degrees, the arc takes up 60 degrees, so I replace the x with 60. I cross multiplied, so I get 360s equals 253.6, and I divided out the 360. They wanted the nearest tenth. Actually, I guess I didn't say. I'm telling you now. Nearest tenth would be 2.1, and it's just a length. It's one-dimensional, so it'd be centimeters. I did the same exact process with the larger circle, So the circumference was 2 pi times 5, which is 10 pi. As a decimal, it would be 31.4, so I put that in for circumference. Still takes up 60 degrees. Did a little bit of cross multiplication, and that is actually a little more than twice as long, which kind of makes sense because this is 2 compared to 5. 5 is 2.5 times 2. So just a thought on that. If they have you round, that's all good. Use your calculator exclusively. If they ask you to put things in terms of pi or keep it exact, there's definitely some things you need to be careful of. So similar strategy here. They give you a sector, it's shaded in. They want this arc length. Notice I boxed in that term. The central angle is 110. The radius is 20. I put that into my formula. Again, S denotes arc length. I'm trying to find that. I found my circumference on the side here. 2 times 20 would be 40. And I left it in terms of 40 pi. I'll tell you why I did that in a second. I inputted the 110 out of 360. And because it says in terms of pi, this is the trick I would say would be helpful. You should have pi in the end. Pi better be there in the end. Okay, at this point in your knowledge of this. So you could say, okay, when I cross multiply, I'm going to leave pi out of the mix for a second. Just do 40 times 110, which is 4,400, then put the pi next to it. You can treat 360s like 360s, and then when you divide 360 out of both sides, be careful, leave the pi. Don't even put that in your calculator, just leave it alone. Only input 4,400 divided by 360, and that will reduce to 110 over 9, and then put the pi in. So in terms of pi, leave it in your equation the entire time, pull it through, do not input it into your calculator. The last example I want to present deals with some of the language of what they're asking for. So it talks about a cart. For whatever reason, you have this cart, it's going around this circular path. It starts at A, it goes counterclockwise to B. Okay. Gives you a radius, and it gives you the central angle. It says, what is the distance? So sometimes this confuses students. So distance implies length. So think arc length, not degree measure. The misconception would is say, oh, it's 165 degrees. Sure, that arc takes up that many degrees of the circle, but what's the actual distance from A to B if I were to measure it? So I put in arc length here to make sure that was clear. Same formula, keep it proportional. I again chose 2 pi r for my circumference. It doesn't say in terms of pi, it says round to the nearest tenth. So I put that in my calculator. but I didn't round to the nearest tenth here. I'll wait till the end. Put that in for circumference, and then 165 out of 360. Quick little cross multiplication. Keep things in your calculator. Nearest tenth brings to 6.9 meters. So we'll continue working on these when I see you in class.